Chapter 13, Electric Circuits. Suppose you had a stationary bicycle that was connected to a light bulb so that when you pedal the bicycle, the energy from turning wheels lights the bulb. How fast would you have to pedal the bicycle to generate enough electrical energy to light the bulb? You would be surprised at how hard you would have to pedal to do something as seemingly simple as lighting an ordinary household light bulb. Some science museums contain this type of exhibit to give everyone a good example of how much energy is needed to accomplish simple tasks in our daily lives. What would your life be like without electricity? You can probably name at least a dozen aspects of your morning routine alone that would have to change if you didn't have electricity. Do you know how electrical circuits work? Do you know what the words voltage and current mean? This chapter will give you the opportunity to explore electricity, electrical circuits, and the nature of electrical energy. Electricity can be powerful and dangerous, but when you know some basic facts about how electricity works, you can use electricity safely with confidence. The vocabulary for this chapter is electric current, electric circuit, circuit diagram, electrical symbols, resistor, closed circuit, open circuit, and switch. Our objectives are to explain how electrical energy is supplied to devices in a circuit, to use electrical symbols to draw simple circuit diagrams, and to distinguish between open and closed circuits. Section 13.1, Electric Circuits. Imagine your life without TV, radio, computers, refrigerators, or light bulbs. All of these things are possible because of electricity. The use of electricity has become so routine that most of us never stop to think about what happens when we switch on a light or turn on a motor. This section is about electricity and electric circuits. Circuits are usually made of wires that carry electricity and devices that use electricity. Electricity. What is electricity? Electricity usually means the flow of electric current in wires, motors, light bulbs, and other inventions. Electric current is what makes an electric motor turn or an electric stove heat up. Electric current is almost always invisible and comes from the motion of electrons or other charged particles. This chapter and the next will teach you the practical use of electricity. Chapter 15 will deal with electricity at the atomic level. Electric current. Electric current is similar to a current of water, but electric current is not visible because it usually flows inside solid metal wires. Electric current can carry energy and do work just as a current of water can. For example, a water wheel turns when a current of water exerts a force on it, as shown in figure 13.1. A water wheel can be connected to a machine such as a loom for making cloth or to a millstone for grinding wheat into flour. Before electricity was available, water wheels were used to supply energy to many machines. Today, the same tasks are being done using energy from electric current. Look around you right now and probably you see wires carrying electric current into buildings. Electricity can be powerful and dangerous. Electric current can carry a great deal of energy. For example, an electric saw can cut wood much faster than a handsaw. An electric motor the size of a basketball can do as much work as 5 big horses or 15 strong people. Electric current can also be dangerous. Touching a live electric wire can result in serious injury. The more you know about electricity, the easier it is to use it safely. Electric circuits. Electricity travels in circuits. An electric circuit is a complete path through which electricity travels. A good example of a circuit is the one in an electric toaster. Bread is toasted by heaters that convert electrical energy to heat. The circuit has a switch that turns on when the lever on the side of the toaster is pulled down. With the switch on, electric current enters through one side of the plug from the socket in the wall, goes through the toaster, and out the other side of a plug. But this is not quite how it works, because when you plug things into the wall, they work on AC power, which AC means alternating current. The current doesn't come in one side of the plug and go out the other side of the plug. All of the electrons inside the wires shake back and forth because it's alternating current that shakes back and forth. Wires are like pipes for electricity. Wires in an electric circuit are similar in some ways to pipes and hoses that carry water, as shown in figure 13.2. Wires act like pipes for electric current. Current enters the house on the supply side wire and leaves on the return wire. Now, this is only true for direct current. In houses, we use AC current. So they're giving a good example, but in reality, our houses don't use direct current, they use AC current. The big difference between wires and water pipes is that you cannot get electricity to leave a wire the way water leaves a pipe. If you cut a water pipe, the water flows out. If you cut a wire, the electric current stops immediately. Examples of circuits in nature. Circuits are not confined to appliances, wires, and devices built by people. The first experience human had with electricity was in the natural world. These are some examples of natural circuits. The nerves in your body are an electrical circuit that carries messages from your brain to your muscles. The tail of an electric eel makes a circuit when it stuns a fish with a jolt of electricity. The earth makes a gigantic circuit when lightning carries electric current between the clouds and the ground. Circuit diagrams and electrical symbols. Circuit diagrams. Circuits are made up of wires and electrical parts such as batteries, light bulbs, motors, and switches. When designing a circuit, people make drawings to show how the parts are connected. Electrical drawings are called circuit diagrams. When drawing a circuit diagram, symbols are used to represent each part of the circuit. These electrical symbols make drawing circuits quicker and easier than drawing realistic pictures. Electrical symbols. A circuit diagram is a shorthand method of describing a working circuit. It is also a model. It is a graphical model, diagram model of an electric circuit. The electric symbols used in circuit diagrams are standard so that anyone familiar with electricity can build a circuit by looking at the diagram. Figure 13.3 shows some common parts of a circuit and their electrical symbols. The picture below shows an actual circuit on the left and its circuit diagram on the right. Can you identify the real parts with their symbols? Note that the switch is open in the circuit diagram, but closed in the photograph. Closing the switch completes the circuit so the light bulb lights up. Resistors. A resistor is an electrical device that uses the energy carried by electric current in a specific way. In many circuit diagrams, any electrical device that uses energy is shown with a resistor symbol. A light bulb, a heating element, speaker, or motor can all be drawn as a resistor. When you analyze a circuit, many electrical devices may be treated as resistors when figuring out how much current is in the circuit. Open and closed circuits. Batteries. All electric circuits must have a source of energy. Circuits in your home get their energy from power plants that generate electricity. Circuits in flashlights, cell phones, and portable radios get their energy from batteries. Some calculators have solar cells that convert energy from the sun or other lights into electrical energy. Of all the types of circuits, those with batteries are the easiest to learn. We will focus on battery circuits for now and will eventually learn how circuits in buildings work. Open and closed circuits. It is necessary to turn off light bulbs, radios, and most other devices in circuits. One way to turn off a device is to stop the current by breaking the circuit. Electric current can only flow when there is a complete and unbroken path from one end of the battery to the other. A circuit with no breaks is called a closed circuit, as shown in figure 13.4. A light bulb will only light when it is part of a closed circuit. Opening a switch or disconnecting a wire creates a break in the circuit and stops the current. A circuit with any break in it is called an open circuit. Switches. Switches are used to turn electricity on and off. Flipping a switch to the off position creates an open circuit by making a break in the wire. The break stops the current because electricity cannot normally travel through air. Flipping a switch to the on position closes the break and allows the current to flow again to supply energy to the bulb or radio or other device. Breaks in circuits. A switch is not the only way to make a break in a circuit. A light bulb burns out when the thin wire that glows inside it breaks. This also creates an open circuit and explains why a burned out bulb cannot light. Section 13.2, Current and Voltage. The vocabulary for this section is ampere, voltage, volt, voltmeter, multimeter, battery, and ammeter. Our objectives are to list the units used to measure current and voltage, to describe how to measure current and voltage in a circuit, and to explain the function of a battery in a circuit. Current is what carries energy in a circuit. Like water current, electric current only flows when there is a difference in energy between two locations that are connected. Water flows downhill from high gravitational potential energy to low. Electric current flows from high electrical potential energy to low. Electric voltage measures the difference in electrical potential energy between two places in a circuit. Differences in voltage are what cause electric currents to flow. Measuring electric current. Electric current is measured in units called amperes, or amps for short. The unit is named in honor of André-Marie Ampère, a French physicist who studied electricity and magnetism. A small battery-powered flashlight bulb uses about a half amp of electric current. Current flows from positive to negative. Examine a battery and you will find a positive and a negative end. The positive end on an AA, C, or D battery has a raised bump, and the negative end is flat. A battery's electrical symbol uses a long line to show the positive end and a short line to show the negative end. Current in equals current out. Electric current from a battery flows out of the positive end and returns back into the negative end. An arrow is sometimes used to show the direction of current on a circuit diagram, as shown in figure 13.6. The amount of electric current coming out of the positive end of the battery must always be the same as the amount of current flowing into the negative end. The example they give is a really bad one. You want to think of it more like people on a slide. When you have a bunch of people on a slide, one person has to get off the end of the slide before another person can go down the slide. They have this in water slides where the lifeguard makes sure that somebody comes out the bottom before another person goes in the top. The same number of people that go down the water slide that get in at the top of the water slide is the same number of people that have to come out the bottom of the water slide. Nobody disappears from the middle of it, and nobody appears in the middle of it. Don't think about steel balls flowing through a tube. That gives a wrong idea of that the electrons push each other through the current. It's not the electrons pushing each other through a current any more than it's the person behind you in a water slide that is pushing you down the slide. You're going down the slide on your own. Each piece of current is moving on its own, and it's because of something else that is making it move. Current doesn't leak out. Electric current does not leak out of wires the way water sometimes leaks out of a hose or a pipe. Electrical forces are so strong that current stops immediately if a circuit is broken. I don't know what it is about it being so strong, but it has to do with the fact that you need a complete circuit so that there is a continuous conducting path from the positive end to the negative end. And if you break it, air is not a conducting path, so then you can't have a complete circuit. Voltage. Energy and voltage. Voltage is a measure of electric potential energy, just like height is a measure of gravitational potential energy. Voltage is measured in volts. Like other forms of potential energy, a voltage difference means that there is energy that can be used to do work. With electricity, the energy becomes useful when we let the voltage difference cause current to flow through a circuit. Current is what actually flows and does work. A difference in voltage provides the energy that causes current to flow. What voltage means? A voltage difference of 1 volt means 1 amp of current does 1 joule of work in 1 second. Since 1 joule per second is a watt, a measure of power, voltage is the power per amp of current that flows. I'm going to say that one more time. Voltage is the power per amp, so how much energy per second for every amp of current that flows. Every amp of current flowing out of a 1.5 volts of battery carries 1.5 watts of power. The voltage in your home electrical system is 120 volts, which means that each amp of current carries 120 watts of power. The higher the voltage, the more power is carried by each amp of electric current. Using a meter to measure voltage. Humans cannot see voltage, so we use an electrical meter to find the voltage in a circuit. A voltmeter measures voltage. A more useful meter is a multimeter, which can measure voltage or current, and that's what we will be using in class. To measure voltage, the meter's probes are touched on 2 places in a circuit or across a battery. The meter shows the difference in voltage between the 2 places. On the left, we have a multimeter that measures a battery's voltage if 1 probe touches each end. On the left, it says the meter reads 0 volts if both probes are connected at the same place. Meters measure voltage difference. The meter reads positive voltage if the red positive probe is at a higher voltage than the black probe. The meter reads negative when the black probe is at a higher voltage. The meter reads voltage differences between its probes. If both probes are connected to the same place, the meter reads 0. Figure 13.7 says a change in height causes water to flow in a pipe. Current flows in a circuit because the battery creates a voltage difference. The top picture shows no height difference, so no water is flowing. In the next picture, you have a tilted pipe, so the height difference causes water to flow. In a circuit, if you don't have a voltage difference, such as a battery or a generator or an outlet, there is no voltage difference in the wire. Once you add a voltage difference, once you add a battery or a source of voltage, then the current flows. Batteries. Batteries. A battery uses chemical energy to create a voltage difference between its two terminals. When current leaves a battery, it carries energy. The current gives up its energy as it passes through an electrical device such as a light bulb. When a bulb is lit, the electrical energy is taken from the current and is transformed into light and heat energy. The current returns to the battery where it gets more energy. You can think of the current as a stream of marching particles, each carrying a bucket of energy as shown in the diagram below. A 1.5 volt battery means that the marchers carry 1.5 joules out of the battery every second, which is 1.5 watts. Batteries are like pumps. Two water tanks connected with a pump makes a good analogy for a battery in a circuit, as shown in figure 13.8. The pump raises up the water, increasing its potential energy. As the water flows down, its potential energy is converted into kinetic energy. In a battery, chemical reactions provide the energy to the current. The current then flows through the circuit, carrying the energy to any motors or bulbs. The current gets a refill of energy each time it passes through the battery for as long as the battery's stored energy lasts. Battery voltage. The voltage of a battery depends on how the battery is made. Household zinc-carbon batteries are 1.5 volts each. Lead-acid batteries, like those used in cars, are usually 12 volts. Different voltages can also be made by combining multiple batteries. A flashlight that needs 4.5 volts to light its bulb uses three 1.5 volt batteries. Measuring current in a circuit. Measuring current with a meter. Electric current can be measured with a multimeter. However, if you want to measure current, you must force the current to pass through the meter. That usually means you must break your circuit somewhere and rearrange wires so that the current must flow through the meter. For example, figure 13.10 shows a circuit with a battery and a bulb. The meter has been inserted into the circuit to measure the current. If you trace the wires, the current comes out of the positive end of the battery, through the light bulb, through the meter, and back to the battery. The meter in the diagram measures 0.37 amps of current. Some electrical meters, called ammeters, are designed specifically to measure only current. Setting up the meter. If you use a multimeter, you also must remember to set its dial to measure the type of current in your circuit. Multimeters can measure two types of electric current, called alternating current and direct current. You will learn about the differences between alternating and direct current in Chapter 14. For circuits with light bulbs and batteries, you must set your meter to read direct current, or DC. Be careful measuring current. The last important thing about measuring current is that the meter itself can be damaged if too much current passes through it. Your meter may contain a circuit breaker or fuse. Circuit breakers and fuses are two kinds of device that protect circuits from too much current by making a break that stops the current. A circuit breaker can be reset the way a switch can be flipped. A broken fuse, however, is similar to a burned out light bulb and must be replaced for the meter to work again.